So a very warm good evening to all. Uh, I am Prithvish Gara. Today I'm going to start a 3-day crash course on theory of computation. Uh, this crash course will cover the entire syllabus required for the exam, and more than sort of building patterns, this teaching you how to solve problems. I'm going to give you a practical sort of framework so that you can solve problems on your own. Okay, so this is designed to be a practical lecture. And without further ado, I'll start day one. So for day one, we are going to study two topics. Uh, First, we are going to study uh, computation. We are going to understand what is computation. Next, we are going to study the computational models, what they are, why, how they are used, why they are built, etc., etc. So I want this to be an interactive session. Can anybody answer the question, what is a computer? Everybody is open to answer this question. Okay, so
A machine which can perform
computer
complex
is
tasks.
basically a machine that takes an input and produces an output. Okay, so it it follows a set of well-defined rules or instructions. Examples of machine include calculator, compiler, and ATM. We as programmers, we basically build computers, right? We write code for calculator, compiler, and an ATM. We write the rules or the instructions so that these uh, machines can become computers. They can compute and solve our problems. What is computation? Computation is basically what a machine does. It is the verb form of the machine. Computation is transforming a certain input and turning it into output using rule. It is a step-by-step process. So what machines essentially perform is computation. Our goal today is to study these machines using abstract models. Okay, we have already studied a real machine. We have studied the architecture of an 8086 microprocessor. Now, today we are going to study computers, but we are going to study them using abstract mathematical models. But still, a question might arise to you. Why do we study theory of computation if we already know programming languages? So, the answer to this is that just as mechanical engineers study the theory of machines, computer scientists study the theory of computation. Mechanical engineers, if you have heard, they study a subject called as TOM. In TOM, they study how physics works on basic mechanical parts like gears, linkages, crankshaft. We don't directly jump in onto an engine. Similarly, we are studying theory of computation to build that sort of intuition. And the practical relevance of theory of computation is that it helps us in these four areas. First, it helps us in pattern matching. We already have studied one of the concepts here, regex. We have used it for password validation. We have used it for email validation. So there is this a concept we have already used from theory of computation. Next is system design. System design includes large-scale distributed systems databases where theory of computation concepts are used. So we have studied something called as a transaction state in DBMS, right? So the failure or success of a transaction depends is not direct. We represent it using states. Those states are essentially computational theory concepts. Understanding limits, possible versus impossible. Some problems in computer science are non-computable, like we cannot design an algorithm for it. Take the famous halting problem. We'll study what it is later on in the course, but even if you have a large data center, you won't be able to solve this problem. The theory of computation helps us uh, understand which problems can be solved and which cannot be solved. And lastly, many CS fields are built on this. So whether you are uh, doing AI or doing something like blockchain, theory of computation concepts are going to be used there in some way, shape, or form. Next, the three pillars of theory of computation. These are the main core subjects inside of theory of computation. And we are only going to focus on automata theory. What these theories ask are different questions based on the nature of computer. So first is automata theory. It answers how machines actually compute. So inside of this, we have our abstract models of machines. We basically ask the question of how machines compute on the most basic scale. Okay, without any sort of external hardware, how do machines conceptually compute? This is what automata theory answers. Next is computability theory. This theory asks the question of what can and cannot be computed. So, like we discussed the halting problem, it can be computed or cannot be computed. This is the question it asks. Likewise, there are many such problems in computer science that computers cannot solve. This is what this theory studies in depth. Last is complexity theory. So, can anybody answer me what is big O timing? We have studied it in previous semester. Can anybody answer what is big O timing? So, big O timing is something that we used to check how efficient we can make a program. If uh, if we have a big O timing of O of 1, that means the program will execute in one iteration. If you have a big O timing of O of n, that means the the program will execute in linear time. Basically, it answers the question how efficiently some algorithm or some program can be computed, whether they can be solved in polynomial or non-polynomial time. Today, we are only focusing on automata theory. Now, in automata theory, these are the core concepts. Okay, so these will come in handy later, but they are very simple. So first is what is a machine here? Basically, fundamentally, a machine is something that processes an input step by step and transforms it into an output. So our CPU is the best example of a machine. It takes an input in the form of assembly code, processes it step by step, and transforms it into an output. Okay, that is how a machine operates on the most fundamental scale. And the machines we are going to study today are based on this behavior only. Next is a state. Now, the all machines have a state. Okay, the humans also have states, emotional states, but machines have the have two basic states: on state and off state. All right. Here in our machines, which we are going to study, they don't have an on or on off state. We logically sort of assign them their states. What states can they be? A state is the current situation or snapshot of a machine at any given moment reflecting its internal configuration. Okay, so we'll see how we define states for the machines we are going to discuss. Next is the most crucial component, that is memory. And memory allows a machine to remember the past inputs and store information crucial for its operations. This is memory allows us to see how which problems can be solved by any given machine. What do I mean by this? We'll see in the next slide. Yes, so this is the most important slide, abstract models of machines. So we already discussed that we are not going to discuss about real machines anymore, like 8086. We are going to discuss abstract models of machines. These computers or machines, I'm using it interchangeably, are basically designed around memory. So let's read each and every one of them. Finite state machine, also called a finite automaton. It has a finite number of states and no memory beyond current state. So uh, it, it is also called as finite automaton. Let's take an example of a traffic light. A traffic light, if we think in perspectives of a traffic light, how much memory does it have? It does not have much memory. It has very limited amount of memory. Okay, it only knows which state it is in currently. So uh, let's say a traffic light is in the stop state. It only knows that it is in stop state. It does not know which state it was in before this state. So uh, if a traffic light is in stop state, it will only know that it is in stop state. The next state it has to go to is the go state, which is depicted by green. So a finite state machine and a traffic light are uh, they sort of work similarly. Where is this used? This is used in simple pattern recognition and text processing. So we will so the problems related to a finite state machine might be finding whether a string ends with some some pattern, or it might be finding whether a number is divisible by some other number or not. So these are the questions they are going to ask with a finite state machine. The problems are not going to be that complex for this. Next is a push down automaton. Now, a push down automaton, we step up with the memory here. We have a stack now. Okay. So let's take the traffic light. If it has a stack as its memory, if we think of a traffic light again with a stack, it knows what state it was previously in, right? So it knows that it was in go state, then it was in wait state. It has previous memory. It can remember all of the past inputs in a structured way. So that actually helps us a lot in solving a little more complex problems like nested patterns and matching parentheses. We'll study in depth what these problems are. Next is a Turing machine. And in a Turing machine, the memory is technically infinite. Okay, so in Turing machine, there is a huge tape, and on that tape, we will read and write. The tape is considered mathematically to be of size infinity. So it has unlimited memory, and this is the model that we use to build any computer program or a software. Is that we assume that it is Turing complete. Okay, so it can solve any and every algorithm that is out there. Okay, so that Turing machine is one of the most important concepts in computer science. Key insight here is that as memory increases, as the memory is increasing here, we are seeing more capability. All right, we are seeing machines tackling more and more difficult problems till they solve almost any and every problem using an algorithm here in Turing machine. Right. So that is one of the core principles here. More memory is means more memory, more capability. Now we'll study on how to design these machines. Okay, in exam they are going to primarily ask us how to design these machines. And before I start, I one trick I have read is to think from the machine's perspective. Okay, so we you might have studied in a subject we have design thinking is that one of the core principles in designing anything is to have empathy, right? So for machine we should have empathy for it. So we should think in perspective of that machine, all right? So this is a really important concept that we'll use, and we'll see how it applies later. Now first machine here, finite automaton or a finite state machine. uh, let's first read an analogy here. Imagine you're on a road trip. So let us imagine that we are all on a road trip and we are driving, and we have turned on Google Maps. Okay, so Google Maps, instead of giving us a map or a route of where to travel and how to travel, it only gives us the directions. So whenever we encounter a dead end, what Google Maps does is it does not give us the entire map or the entire route. It only tells us whether you should turn left or whether you should turn right. Okay. So that is a strange thing. But if we look at ourselves as if we look at final automaton, it basically works like this. It knows the state in which it is currently in. So we know whether or not we are taking a turn, whether or not we are moving forward, whether we are moving reverse, or whether we are parking our car or not. Okay, we know which state we are currently in, but we do not know the map. Okay, we do not know the next set of inputs that are going to come. And this is how basically a finite automaton works. It does not have any memory except the fact that it is which state it currently is in. So let's read it. Imagine you're on a road trip. Your co-pilot gives one instruction at a time. Turn left at the next light. You execute it, arrive at the next point, and immediately forget the previous turns. Only your current location dictates the next action. Okay, so it you do not have memory of whether you took turn or whether you were walking straight, whether you are driving straight or whether you are driving reverse. You only know the next input and how to drive, what to do for that input, whether or not you should take turn or move forward or not. So let's see how this applies to the formal definition. M equal to Q sigma Q capital F and delta. This is a phi-set tuple. We all know what a tuple is. A tuple is an immutable data structure. All right. We cannot change the elements inside of this tuple. What it what are the elements in this that we have to define? First is capital Q. Capital Q contains a finite set of states. So if we are going to define the uh, finite automaton here, which is driving our car, the finite set of states it has is are basically four. It can either drive forward, it can drive reverse, it can park the car, or it can turn. All right. So here we have defined the finite set of states in which our driver can drive. Okay, this is how we define it formally. First, we define the states in which the finite automata can be in. Next is sigma. Now, what is sigma? Sigma is a set of alphabets or inputs, left, right, straight, back. So simply take the Google Maps here told us to give us the input of moving left, right, straight, back. Okay, and that is the basic concept here. It's that it only gave us the input, and we had to decide which how to process that input. Okay, so finite automaton here, it will only receive these four types of inputs. Okay, so in formal definition we define what inputs or alphabets in theory of computation as they are called the finite automaton will receive. Next is q, a designated start state or a starting point. Now can anybody answer, whenever you sit in a car, what is the start state of that? What is the start state of the driver of the car? Whenever you sit on the driver's seat, what state is the car in? So car is in park state. It is as simple as that. Whenever you sit in a car, it is in a park state. You start a car, but whenever you sit in a car and start it, you're in the park state, right? You have to then change the gears and then move forward. But whenever you sit in the car, it is in the park state. So it is the uh, start state which we have defined for the car. Here it is starting point, which is wrong. But whenever you sit in the driver's seat, the start state is that it is in the park state. Okay. Next is capital F, one or more accept states. So see, let's take for example that uh, we have reached our destination, and the Google Maps, what it does is that it understood that you have reached your destination. If now once we have reached the destination, we will obviously not, let our car move forward or take a turn or anything. We will park it. So the fine except state here, or the final state we want our car to be is the park state. Okay, it is as simple as that. Next is delta, or a transition function. Rules for moving between states based on input. So we saw the four states we have: forward, reverse, park, turn. Okay, and we saw how we process that input. But for that to happen, we have to use logic, and we have a brain. But finite automaton does not have that brain, right? We have to give it that logic to say, if you encounter left input, then what state should you be in? That is basically how we define the transition function here. So we'll see how we define it. We use it using a table, that is a different thing. But finite automaton, these five elements we have to define. And a finite automaton has no external memory beyond its current state. It is used to recognize a regular language. So this is a regular language we'll see in the next lecture, but it has zero memory, as we've seen. It does not know whether it took a turn or not. It has no external memory. It has the memory that it is in the current state. That is it. So it can recognize a regular language. What it is, we'll see later. Now let us distinguish between a deterministic and a non-deterministic finite automata. So can anybody tell me what is the difference between deterministic and non-deterministic? A deterministic is some event that we can predict, right? We can think of whether it is going to rain tomorrow or not based on what the weather report tells us. It is deterministic. Non-deterministic is we cannot define what that input might be. Okay, so here they have given the analogy like a traveler given one clear direction at each intersection. A DFA always follows a single unambiguous path for a given input. Okay, so DFA, whenever it receives an input, it will follow, it knows which state it will be in, and that is, and that state is predictable for us. Okay, so it is deterministic. For each state, and put simple, there is exactly one transition. That means deterministic. That whenever it receives an input, there is exactly one transition. We know where it is going to move. So next points are that it has no ambiguity in computation path. See, whenever we think of how a finite automaton might process an input, we have no ambiguity. We will have no confusion on how it is going to process it. So it becomes easier to implement and analyze. Now, what is non-deterministic? So let's take the road trip analogy we discussed earlier, and let's say that uh, we are in this chalk, okay, and I hope you all can see this. We are in this chalk, and our car is coming from here. Our vehicle is coming from here, and let's say we are this car, okay. Now we are this. If we are this car, and we have Google Maps turned on, we will. It will. Let us say that it will tell us to move left. Okay, it will tell us to drive in the left direction. Now, thing is that we can either move we can either move left here, or we can drive here, and we can take the next left. Okay, now this creates a problem. Okay, let's say there are two lefts here. Okay, this will create a problem in determining which path the finite automaton will take. Okay, so whenever there are multiple paths, we assume that a finite automaton will take multiple paths simultaneously. Now that sounds confusing, but conceptually it is that whenever we think of designing something, we think in terms of what are all of the possible paths that machine can take. Okay, so this is something we keep in mind when we are designing a non-deterministic finite automaton, is that we do not know when it will take the turn. Okay, it can move straight and take a left turn, or it can directly take the next left turn. That is not in our hands. So what we do is that we determine all of the possible paths a machine can take at any given input. Okay, we have written here conceptually tries all paths in parallel. We'll see how it applies to when we are designing machines. And a non-deterministic finite automaton, as you said, is not simpler to design for easy patterns. But when we see more complex patterns, like edge cases or patterns with a little more complicated uh, patterns, a non-deterministic finite automaton becomes simpler to design. Okay, so a DFA. So the last point is something I want you all to remember. It's that in deterministic finite automaton, we start with the assumption that the finite automaton has already read an input. Okay, and a non-deterministic finite automaton, we start with the assumption that the finite automaton has not yet read an input. This will become clearer when we are designing, but the start state of a deterministic finite automaton, when we are designing it, we assume that it has already read an input. Okay, we already assume what the first input will be. A non-deterministic finite automaton does not know that. That is something to keep in mind. And key insight here is that despite the apparent differences in their behavior, DFAs and NFAs are equivalent computational powers. Any language recognized by an NFA can be recognized by a DFA. So any problem when we try to solve, we a non-deterministic finite automaton, let's say if it solves a particular problem, a deterministic finite automaton, a DFA, can also solve it because they have same computational power, right? We already discussed what computational power means. Whenever we increase the memory in our machines, computational power increases. But since DFA and NFA have same computational power, they can solve each other problem. How we'll see later. That is a separate concept. Now, next machine we are going to discuss is a push down automaton. Now, what is push down? Push down is basically something that we basically an action, right? We take an item and we push it down into something. So Fulton automaton is a stack based machine. It will take an item and it will push it down something. It will push it down instead of a stack. Okay, that's why it is called push down automaton. It takes an item, a symbol, and pushes it down something. Now let's understand what this is using an analogy. Let's say you're in a library and you have been given a book to see if it is in the this scattered book set or not. So let's say you enter the library and there are books all over the tables which are scattered. You have been given the task of finding whether for a given book set max all of the volumes exist or not. Okay, so if you have uh, let's say the book sets, they are not properly arranged. You arrange them in a sequential order. You arrange them sequentially and you start to read their names one by one. Okay. Now let's say you have arranged the books like this. Okay. And the first book you pick is volume 1 max. Okay. So what you do? The first book's name is volume 1 max. What you do is in the list here, in the stack, it's called it stack. You take this book, right? Volume 1 max. You take this book and you push it down. Okay. You push it down. M1. Now, what does this do? Okay. When imagine you have this book set and you're reading it sequentially from left to right. The first book you get is volume 1 max. You write, you try to track in how many books you have encountered from this set. Okay. So you encountered volume 1 max. Okay. So you encountered the first book in this three volume set of maths. All right. So what you do is that you push down in stack a symbol. Okay. We have pushed down in stack a symbol. What is the symbol? M1. This is used to indicate that we have found the first volume of this book set maths. Okay. We have found the first book in this book set called maths. Now we'll take the next book, and it is volume 1 physics. Now we it does not matter to us because we are trying to find the next volume in this maths book set. So this input we ignore and we take the next input, volume 2 biology. Volume 2 biology also does not matter to us. So we'll read the next input, volume 2 maths. Now here we see that this book belongs to the book set maths. Okay, this book belongs to the book set maths and it is the second volume. Okay, so what we do here is that in stack we push down another symbol called M2. Right, so you're seeing that this stack allows us to track as a push down automaton. This stack allows us to track what books we have found in this book set. Okay, it allows us to track and we write it here. Using a symbol, we write here what books we have encountered. Okay, it helps us to track. Now we'll read the next book, volume 3 physics. It does not matter to us. We'll read the last input, last book name, volume 3 maths, and we'll write here M3. So what these symbols indicate is that we found the first volume of book maths, we found the second volume of book maths, and we found this third volume of book maths. So as we kept on tracking this, as we went on taking input, we tracked what book we have found in this scattered book text. Okay, so this essentially what stack did is it helped us find which book of this book set maths we have currently encountered. Okay, that is the basic concept of a push down automaton, is that it helps us find which book of which book exists. Like it helps us track our dependencies, right? When we encountered, when we saw this input, when we saw the first book, book volume 1 maths, it created a dependency inside our head to find the next two volumes of books. Okay. And when such a dependency is created, we have to track it down, right? Let's say the input size, let's say there are 100 books, and within 100 books, you have to track whether or not you have found this three volume book set. Now that it becomes difficult to track, right? We cannot remember from like 100 books which books were of maths, which volumes they were, etc. etc. So we use as finite automat as sorry as push down automaton. We use a stack to sort of represent which books we have found and which books we have not found. It is a simple concept. Now, formally, we define it using a 7-set tuple. Okay, not a 5-set, a 7-set tuple. Some of the things we have already seen from finite automaton, they appear here again. So Q is the finite set of states. Sigma is the set of input symbols. Now this half-shape T symbol here, it represents the set of push down or stack symbols. Okay, so here we see that M1, M2, M3, these are symbols we use for the stack. Okay, these are not the symbols we sort of use with input. We use it in the stack to represent what the input tells to us. Okay, so this is a push down or a stack symbol m1, m2, m3. Whenever we are defining a push down automaton, we have to define what are the set of symbols we are going to use. In this case, M1 represents the first volume of the book, M2 represents second volume, M3 represents third volume. These are symbols that we have defined. Next is Q0 initial state. We have already seen what this means. Z is initial stack symbol present in the stack. So you might have observed here, we have written Z here. Z represents whenever we start any operation in push to automata, it Z is always present. It represents that stack is empty. Then F is the set of final states, right? So we all saw it in final automaton. What is the final state we want our automaton to end? So this we have already seen. Delta is a transition function that maps Q times sigma union epsilon times bracket times half shape t arrow t bracket q times half shape t star. Now, what does this mean? This is of the push down automaton. Now, I this we will discuss later what this means because this symbol here, star symbol here, it is related to uh, languages and grammar, regular operations. We'll see what this star symbol represents later on tomorrow, basically. Now, this is asked in the syllabus, so I'm going to discuss it. Define a push-down automaton as a generator, as an acceptor, and as a decoder. So we saw in finite automaton that it was an acceptor, right? It was an acceptor of a regular language. If let's say I spoke a sentence in an English language, in the English language, and I told you to uh, I asked you whether this sentence belongs to the English language or not. You will obviously, based on what you have learned about the English language, tell whether it is of the English language or not. So the final automaton is also an acceptor, and a pushdown automaton is also an acceptor. It for any input string, it tells if it belongs to a specific language or not. So that a pushdown automaton already does for context-free languages. That so we have no problem in that. Now, next is a generator. So unlike finite automaton, which a finite automaton does not have any memory, right? So it cannot say anything. It only knows which state to move to. Because push automaton has no memory, it can generate strings as well. Okay, so as we already have, as we already know, push automaton accepts strings in the context-free language, and it also generates strings that belong to a context-free language. And this we see in compilers a lot, computer compilers, programming compilers. We see context-free grammar is used, and how a push-down automaton does this, how it becomes a generator. We'll see later. It uses something called as production rules. Okay, we'll see later how push-down automaton works as a generator, but take it for a fact that it will generate strings that belong to a context-free language. Lastly, it is a decoder. Now, how it is a decoder? Let's say I gave a push-down automaton and this paragraph. Okay, and I asked a push-down automaton to find the number of sentences in this paragraph. So let's read this paragraph. Push down automata are more powerful than FSMs because they have a stack memory. Okay, this is one sentence. We encountered a this thing, a full stop here. So we'll write it in the stack that we encountered a sentence. So let's say we when we encounter to a full stop, it becomes one full sentence, and we write in the stack S1. All right, now let's read next sentence. This additional memory allows them to build structures, check structures, and interpret nested patterns, forming the current basis of many programming language features. Now we encounter another full stop here. Okay, because we encountered two full stops here, we immediately conclude that this paragraph contains two sentences. A pushdown automaton uses a stack to say how many sentences are in a paragraph. Okay, it solves questions like these. It can also answer the question of whether how many brackets are there. So, like, let's say uh, it reads this word and it encounters an open bracket. Okay, and we asked the push down automaton to say whether or not this is whether it or not this is a this bracket will close or not. So push down automaton, whenever it reads the paragraph, whenever it sees a open bracket, it will also try to find a close bracket. Okay, whenever it sees an open bracket, it will write it in the stack that there is an open bracket. Okay, let's say it in the stack it writes O. Whenever it encounters a closed bracket, that dependency which it had earlier, that question which it had earlier, whether or not this uh, bracket is closed or not, whether or not this word is closed or not, that dependency of it is resolved. So in this stack, we will pop it. Okay, the O we have written, we will pop it. Right? It is simple. You might have already sort of seen this in programming languages as well. Whenever we are writing some for loop in C, the compiler will check. See, because PDA is also using compilers. The compiler will check whether or not each and every stack symbol, sorry, whether each or and every round bracket, open round bracket is closed or not. Okay. Uh, so if I write a for loop here, the compiler will check if this stack is, sorry, if this round bracket, open round bracket is closed or not, right? If I give this to a compiler, obviously it will not compile. Okay. So push down automaton helps us do that. And yeah, that is why it is, we also call it as a decoder. Now, before we dive into Turing machines, I hope that you all understood all of the concepts we have discussed here. Let's have a quick revision. So, a finite automaton has a, is of two types: a deterministic finite automaton and non-deterministic finite automaton. So, whenever we solve practically uh, in the exam, they will either tell us to draw a deterministic finite automaton or a non-deterministic finite automaton. Okay, it is defined formally using these elements Q, sigma, Q, Q naught. So I have not written zero here, but it is Q naught, capital F, and delta. And a push down automaton, uh, it is defined using seven states. Okay, it uses a stack, it has memory, and it is defined using seven elements in this tuple. So it is Q, sigma, half T, delta, Q naught, Z, and F. Okay. So these things we are going to use whenever we are solving problems based on DFA and PDA. Now, a deterministic finite automaton, just like how a finite automaton has two types, a Poisson automaton also has two types, which we'll see later. Now I want to solve some problems here. So let's take uh, let's solve some problems here practically so that you understand some of the concepts used. Design DFA that accepts strings with at least three A's. Okay, what does this mean? So here they have given us sigma. Sigma is basically the alphabets which we are going to use in this string. So uh, here we have a string, let's say A, B, B, A. DFA does not have any memory as we know. The DFA does not have any memory. But the question asks us to find and accept strings where it at least has three A's inside of it. Okay. So if a DFA does not have any memory, how do we do it? Okay. So let's think in perspective of DFA, how we will solve this problem. Let This is our input string. Okay. This is an example. Let's take this as our input string. DFA will not a DFA will usually know what is the first input. Okay, so a DFA here, I mean, we have to assume that the DFA knows what the first input is. Okay, so a DFA, let's say it reads the first input here. We have to assume what it will do whenever it reads the first input. Okay, so whenever so before it starts reading the inputs, we write we give DFA a state called as Q0. Okay, the Q0 state, in Q0 state we say that a DFA has not yet seen anyone. Okay, so a DFA whenever it sees an input, we assume that a DFA has read an input and it has not yet seen anyone. Okay, so whenever we start the machine, DFA will be in this state Q0. That's why see we have represented this with an arrow here. Whenever the machine starts, it will be in Q0 only. Okay, it will not be in any other state. It will be in Q0 as a start state. That is fixed. We will not change this. DFA is in Q0. Now whenever so now DFA in ADFA, let's say it encounters the first input A. Okay, it encounters the first input A, and now the DFA it does not have any rule set. Okay, yet it does not have any logic which state it has to move to. Our traffic light had some logic built in that said that if you are in stop state, go to the go state. But the DFA right now it does not have any logic. Okay, so what we'll do is that we will first define the states. Okay. Um, Sorry. Yeah. So let's remove these. And yeah, so this is these are the set elements of any finite automaton. Okay. We'll write this with D. And DFA, it, we have to define these five elements for any given DFA. Okay. So we first take this element states and we sort of define along the way as we are processing input with the DFA, what are the states it will be in? Okay, we do not know how many states to define yet. Okay, we only know that DFA is processing input, and we have to tell which state it has to move to. Okay, we have not even defined final or accept states. We only know that DFA is processing inputs. Okay, so imagine that DFA is asking us the question of which state it has to move to next. So states Q, states it is represented here using a Q. So we write here Q for short. Okay. Next, we have uh, next sigma. It is already defined. Okay. So alphabets we say here. It is already defined. It is A and B. Okay. Any input we will receive, it will either be in the form of A or B. All right. It will if any DFA except if any input has, let's say, C in it, then the DFA will not accept it. So this is something which you have to remember, that DFA will only accept input within the alphabets here. Next is Q naught. So we have already defined here what is the Q naught. Q naught means the start state. Start state. So we started is DFA with an assumption that DFA has not yet seen any one. Okay, so it has not yet seen any, sorry, not one, it has not yet seen any A. Okay, whenever we start with Q0, it has not seen any A yet. Okay, so Q0 represents the fact that a DFA has not yet seen any A. So we'll write start state Q naught as Q naught. A, same symbol. Next is delta. Now delta for a finite automaton, we define it using a transition table. Okay, so how do we write a transition table? Let's say let's take a state here. Let's write state here, and let's write the input here. Okay, so we'll write state as the uh, as a column, and we'll write the inputs of the DFA as a row. So let's write it here. Q0 is one state, and we are arranging this input, and we are arranging the inputs and the states. The DFA is going to be in matrix format. So yeah, let's make an actual table. So, yeah, so state. So we'll write DFA here, or let's use blank. This is Q0. Okay, this is the states here. Okay, these are the states, and this is the input the DFA is receiving. Okay, we can easily find what inputs any DFA will receive using alphabets. Now this is the input a DFA is going to get. A. Let's say now we know that DFA is in Q0 state. We already discussed this multiple times, and we already know that it does not know whether or not it has, and we already know it does not know yet whether it has seen an A or not. Okay, a DFA basically things like that. It does not know yet. It does not know what to do. It will take the next input and it will see this transition function and see where to transition to next. So DFA has taken input and it is asking us which state to move to. Okay. So when we read this that DFA is in Q0 state, we know that it has not yet seen any A. Okay. After the DFA sees an input, after the DFA reads an input, let's say it reads here the fact that it has encountered an A. What do? We tell the DFA to move to the next state. Okay. We tell the DFA does not know. We tell the DFA to move to the next state, which is Q1. Okay. So the DFA moves to the next state Q1. And this Q1 state represents the fact that for us, it represents the fact that DFA has seen at least one A. Okay. It has seen at least one A. We for a fact know that DFA does not know it, but we know that whenever DFA is in Q1 state, it has seen at least one A. Okay. DFA only cares about which input, which state should it move to next. So whenever DFA will ask us which state should it move to next, we read the state which it is in, and from that we will logically decide. We will help the DFA move to its next state. Okay, so now it is in state Q1. If it encounters, let's say, instead of A here, it finds a B. Okay, the first input here is B. So a DFA, what it will do is that it will stay in the state Q0. Why? Because as it is reading the input sequentially, okay, a DFA does not know this. Okay, let's DFA does not know the rest of the input. It has only encountered the first input here. Okay, this input. So let's say it encounters B as its first input. It does not know the rest of the input, unlike us. So whenever it encounters a B, it will remain in that state. Okay, it's simple. When DFA sees A, it will move to the next state, and whenever a DFA sees B, it will remain in the same state. Okay, that is the simple logic here for designing this. And now we will similarly do this for the rest of the states. Whenever it sees an A, it will move to the next state. Why? Because the next state, it represents for us the how many A's it has encountered. Okay, the DFA cannot count, but from the states we know how many A's the DFA has encountered. So DFA has seen at least three A's is the final state we want to be in, right? Let's write here final state F. The final state a DFA is should be in is Q3. Why? Because Q3 represents the fact that the DFA has at least encountered three A's. Okay, so let's let's fill in the rest of the transition table. Uh, so this will be in Q1. This will be in Q3. and this will be Q3. So whenever, so let's say DFA has read this input, and DFA has encountered has found that this string considers uh, this string contains three A's. Okay, so wo- so why have we written here that when the DFA receives the next input B, it should stop? So simple thing you have to remember is that a finite automaton or any machine, it has to read each and every input. Okay, so it cannot stop whenever it encounters three A's. It has to read each and every input. Okay, in Q3 state, we know that a string at least has three A's. We do not have to read any input, but for a machine, whenever we are defining a machine, we have to write which state the machine will move to, when which state the machine will transition to whenever it encounters the next input, right? Is as simple as that. So a DFA, or it encounters B, it will be in the state Q3. Okay, so this solves the problem. This is the diagram for the DFA. When it encounters the input ABB, AAB, let's say, it will be, first and foremost, it will be in state Q0. It has not yet seen any A's. If it sees an A here, reads an A here, it will move to the next state Q1. Okay, now here it reads input B. Okay, it will stay in the state Q1 only. Okay, it will not move. It now it reads takes the next input. It is B. It will stay in the state Q1 only. It reads the next input A. It will move to state Q2 because now it has read two A's. We know that it should move to state Q2. Okay, and it reads the next input Q3. Okay, so now it has read three A's. We know that it should move to Q3. That's why we written here Q2 on receiving input A will move to Q3. And if Q2 receives, and if machine is in Q2, and if it receives an input B, we know that it will stay in Q2. Okay, it is simple, and yeah, it will. We know that here machine will be in Q2 state, and if machine is in Q3 state, we know that it has encountered three A's. Now, if it finds a B at the end, okay, when it reads an input and it finds a B at the end, it will stay in the same state. Okay, this is the basic logic of this machine. Nothing complicated here. Next, we have to design an DFA to accept strings of zeros and ones. Okay, so what they have already given here. Okay, this is type of a word problem. What information have they given here? They have told us that we have to design a DFA. Okay, they have written octane here, but it is design. We have to design a DFA that is going to accept strings of zeros and ones. All right. We know that the strings we are going to receive are going to contain zeros and ones. So they can be like this, or they can be like this. All right. These are the type of strings we are going to receive. Okay, so they already given us the information of what is going to be sigma. Okay, set of alphabets that here, what symbols they are going to use for any input. It is going to be 0 or 1. Okay, now next, what they have told us: design DFA to accept strings of zeros and ones. with even number of zeros and even number of ones, right? So whenever we receive a string with these um, input symbols, these alphabets, we have to decide whether they contain even number of zeros and even number of ones. Okay, so it should, let's say, this is a string here, 0011. We have to accept DFAs with with even number of zeros and even number of ones. Okay, so it can be a string like this where we know that there are even number of zeros and even number of ones, or it can be a string like this as well, where there are again even number of zeros, but they are not um, sequentially aligned. I hope all of you are getting this. Okay, so it has to, our DFA has to find out and reject certain strings. Now here in this string, it has to reject it. Why? Because it has found even number of zeros and even number of ones. So we have to track two things here: number of zeros and number of ones. A DFA does, as we know, it does not have any memory. So how do we do this? Well, we start with an assumption. Okay, whenever we design DFA, we start with an assumption of what the first input is going to be. So let's uh, take a string here. We are starting with an assumption of what the first input is going to be, or we are starting with an assumption of what is the logic going to be here used here. Okay, so here Q0, what it does is that Q0 is an state, it is start state. Q0, it tells us that DFA has not yet read any input. Okay, DFA has not yet read any input, but yeah, it is in the it has not yet read any input, but it is in this state. It is even, it has even number of zeros and even number of ones. Okay, now let's say it reads the first input here. It reads the first input 0. What happens here? Uh, we first assume that when it reads the input, there are even number of zeros and even number of ones. Okay. When we read the first input, the balance shifts, right? So if I were to write it down, there are even number of zeros in a string, even number of ones in a string. Okay. Then there are odd number of zeros in a string, even number of ones in a string. Then there are even number of zeros in a string, odd number of ones in a string, and there are, and then there are odd number of zeros in a string and odd number of ones in a string. All right. Whenever we start uh, this machine, we are assuming that it should, that the string should have even number of zeros and even number of ones. Okay. Uh, Here it is very simple assumption. Okay, we assume that when there is no input, okay, let's say this input is not there, there we have not yet seen anything. We have the DFA has seen even number of zeros and even number of ones. Okay, This is our starting assumption, and whenever DFA starts, it asks us which state to be in. We'll say be in the state Q0. Why? Because in Q0 state, we assume that there is there are even number of zeros and even number of ones. Right. Now, when it moves to Q1, now when it reads the input 0, okay, when it reads the input 0, what will happen? The balance will shift. Okay, when it reads the input 0, what will happen is that the balance will shift for us. Now there are odd number of zeros. Okay, there are odd number of zeros and there are even number of ones. Even though we haven't seen a one yet, we assume that there are odd number of zeros in the string and even number of ones. Okay, based on the input we have received, we are telling DFA, look, we have encountered 1 0, right? So be in the next state where we have said that this represents odd number of zeros and even number of ones, right? Each state we define here represents what it means to us. Right now, DFA is in this state. It knows that we know that DFA does not know, but it knows that it is in Q1 state. We know that from the first input, okay, forget rest of the input. From the first uh, input, it is odd number of zeros and even number of ones, even though we haven't read anymore. Our assumption has changed that maybe in this string there are odd number of zeros and even number of ones. Now it receives the next input, 1. Okay. When it receives the next input, 1, the assumption again changed, right? We were in state Q1, right? After it receives the input 1, we know that it is that there are now odd number of zeros and odd number of ones in the string. Okay. Based on what we have seen, we assume that inside of the string there are odd number of zeros and odd number of ones. Okay. This we have made this assumption. So when Q1 asks, I am in state Q, sorry, when machine asks if I am in state Q1 and if I receive the input 1, what should I do? Uh, you We tell the machine that you will be in another state where there are odd number of zeros and odd number of ones. Okay, this is all. Now this is based on the input we have received that there are odd number of zeros and odd number of ones in the string. Okay, we assumed first that there are even number of zeros and even number of ones, right? Now that assumption has changed for us, and now from inputs we have received, we have told the DFA that maybe there are odd number of ones and odd number of zeros in this string. Let's take the next input. Okay, in this string, we'll take the next input. Here, our assumption changes again. Okay, our assumption has changed yet again. Now we know that there are even number of zeros and odd number of ones. Okay, so we know that there are even number of zeros and odd number of ones. Right. Whenever so DFA now before this was it was in Q3 state. We told it to move to the Q3 state. Now DFA it reads the next input 0. It asks us if I'm in Q3 state and if I encounter a 0, which state should I move to next? Okay, DFA is asking us this question. Now, if we now we know that there are from this string, from what we have seen, there are even number of zeros and odd number of ones. Okay, we know this. We know for a fact that there are even number of zeros and odd number of ones. So what we do here is that when the uh, when there are even number of zeros and odd number of ones, we tell the DFA to move to the Q2 state. Okay, we tell the DFA to move to the Q2 state. Right here, it will move to the Q2 state, and it will then see the final input. So let's write the final input as 1. DFA is in Q2 state. From from when DFA is in Q2 state, we know that up until this point, it has encountered here even number of zeros, two zeros and one one. Okay, that from the state we know. So now because we know that DFA has this, whenever when it receives the next input one, we now get the idea that there are even number of zeros. Okay, there are two zeros and there are two ones. Okay, this for us it is clear, right? For us it is now become clear that there are even number of zeros and then there are even number of ones. Okay, so when Q2, so when machine is in Q2 state and it receives a one, logically we know that there are from the past input that it is that there are even number of zeros and ones in the string, right? So in short, finite automaton based on the state it is in, we know that what inputs what inputs it might have encountered earlier and what inputs we it might encounter less. We the only thing we tell it to do is uh, we tip the balance, right? All we do here is we tip the balance. I mean, it is simple, right? Whenever something is, whenever we encounter something that has an odd count, okay, let's say three, and if we find, if we add one to it, it will become four, okay. If we have encountered uh, three ones here, okay, if we have encountered three ones here, we know for a fact that if we encounter another one, then there we can conclude that there are even number of ones in the string. All we are doing is tipping the balance, right? We are changing one thing here. We are only switching these two things, even odd. Okay. So if we add buttons here, then uh, we could define it something like this: zero, odd number, or even number. One, odd number, or even number. Okay, only we are only tipping the balance. We are choosing which how many number of zeros and how many number of ones are there. And based on the combination of buttons we can click here, right? Combination of these four buttons we can click. Based on these combinations, we have defined the states. Okay, we have defined the states here, and Q0, Q1, Q2, Q3 are these four states. DFA should, we are designing a DFA such that whenever it is in a particular state, it will move to the next state. Okay. So if it is in state Q0, we tell the DFA, this is the this thing, right? This is the transition table. We represent this with delta. So yeah, basically whenever a DFA uh, it is in the Q state, it will look in this transition table and it will see which state should it move to next. So if it is in state Q2, we know that we had already discussed that if it is in state Q2, there are probably even number of zeros and odd number of ones. Okay, when it sees another zero, we know that it has odd number of zeros and odd number of ones. Okay, but when it encounters an input one, there are even number of zeros and then there are even number of ones. Okay, so in this transition table basically includes what we have discussed here. What are the four states we have defined here? Okay, okay. Now based on this, we have to draw the diagram, draw the transition diagram, and it is quite simple to draw the transition diagram here. So let's remove this and let's define four states here. And yes, so uh, yeah, so Qi to Q0. Qi to Q0. Okay, this is the start state we defined here. Start state Q0. We define this as the start state. Next, we have to see on input 0 where it will move. So on input 0, it moves. Yeah, so here we defined Q0 as start state. On receiving the this thing, on receiving input 1, we tell it to move to Q1. Okay, here in transition table, sorry, yeah, you will tell it to move to Q2. So we have to follow the transition table, and likewise we have to define we have to design and draw the diagram here. So Q0 will move to Q2, Q2 will move to Q3, Q2 will move to Q3 on receiving input 0, and Q0 will move to Q1 on receiving the input 0. Right. So yeah, basically we take this transition table and from it we draw a transition diagram based on the connections here. So I hope it is clear for all what we have discussed here. We will take a break of 5 minutes and then we'll see the later problems to discuss like Turing machine problems and NFA to DFA and NFA problems. So we'll meet after 5 minutes. Okay, so I will continue on the next set of the problems. Uh, now we are going to now we'll try to solve the NFA problems. And NFA, as we discussed, is non-deterministic finite automata. And how it is non-deterministic, we'll try to see what is its nature. So uh, let's let's read it. Design NFA that accepts strings starting with A and ending with A, or starting with B and ending in B. So uh, yeah, so I already told you that in NFA, whenever we uh, start, okay, we have no assumptions yet. And why is it that? It is that whenever we start reading an input in NFA, it creates these two branches, you know, and it is difficult to define here, but basically, if uh, I were to say that if I were given a problem of designing a finite automaton, it will and I have to see whether the string starts with an A and ends with an A, or starts with a B and ends with a B. I cannot make an assumption here. So because I cannot make an assumption, the how I'm going to start uh, my NFA is the start state of the NFA. I'm going to define for myself is that I have no assumption here. Okay. So A B B A or B A B. Okay. The start symbol could have been anything, A or B. So whenever we start this machine, Q0 should be something that uh, has no assumptions. Okay. So no assumptions. Now let's say from Q0, I will draw a table here. Just a minute. One. And in Q0, we do not make any assumptions. Okay. In DFA, we did make an assumption here. Okay. Whenever we designing a string to accept even number of zeros and even number of ones, we started it in a state where we knew that there are even number of zeros and even number of ones. Okay. Here also, we started with an assumption that it has not yet seen any A. So string must be must have zero A's. Okay. This is still an assumption. Okay. It might seem like common sense to us, but it is an assumption. In NFA, there is no assumption. We did not begin with any assumption of what the start state should be. Okay. Whether should be A or whether it should be B. There are no assumptions here. Now let's take Q0, and Q0, it is the start state. When it reads an A, when it reads an A, it will move to the state Q1. Okay, it will move to the state Q1. That does not mean that it has read all of the symbols. We already know that if we only know that it has encountered an A, so we tell the final automaton to move to state Q1. Okay, now final automaton is in state Q1, but and let's say we are in Q1. Okay, now final automaton encounters a B. It asks us whether it which state it should move to next. So we know that we because up until now, because we have read A and B only, A and B, the string starts with an A and ends with a B. Okay, so this we already know. Okay, it starts with an A, but we do not know if it ends with an A. So we tell the final automaton to uh, move to the state Q2. Okay, why? Because sorry, Q3. Why? Because this states that sorry, this states that we have we started with A, even though we have encountered a B, even though we have encountered a B, it will um, it will be the last symbol. Okay, it will be the last symbol and it will be accepted. Actually, sorry, this is reverse Q2 and Q1 is so yeah. When you start with Q0, we know that string started with A. Okay, and because we encounter an A, the string this will be the last symbol. Okay, that we have that we are making this guess we are making after we encounter the first state. Next state is Q1. Now this state we tell the final automaton to move to because we do not know what is the uh, end state, but we have found B. Okay, so this is a little complicated to understand, but basically when we started this machine in Q0, when we encountered A, we saw an A and assumed it to be the last symbol. Okay, we assumed it to be the last symbol, so we then said Q2. Okay, but when we encountered a B, it we do not know what is the end state, but we have found a B. Okay, so which these are creating two paths. Okay, these are creating two branches of for our assumptions that the string started with A, so it must end with A. The string started with in B, so it must end in B. All right. Now we are in the state. Now we are in the branch where we are assuming that because it started with A, it should end with an A. That is what we have to think here. Whenever a string is starts with an A, we want final automaton to end on a state where it assumes that A is the final input of the string. Okay, so this is the first branch, right? This is the first branch. and second branch is when which have started the machine, and we have started the machine Q0. In Q0 we have encountered a B. Okay, we have encountered a B, and we have assumed that from this put that B must be the last symbol. Okay, so we are making assumptions here. We do not yet know the full string, but when the state is in Q0 and we have encountered a B, we are instructing the machine to move to the state Q4. Right now, this will now once we encounter an A here, once we encounter an A, the machine will we will assume that the machine started with an B, but will and it will end with a B, but but because we have encountered an A, we do not want our machine to end uh, on this as the final state. Okay, the machine only checks the input and knows which state it has to move to next. Once the input ends, the machine will not move to magically move to like the correct state, the final accept state. So how we assume it is that when the first symbol is B, the next symbol, if it is an A, we tell the machine to not be in the state Q4. Why? Because Q4 is the accept state. Okay, Q4 is an accept state. It assumes we read the first symbol, and our assumption was that it this is the final string. Okay, and Q4 is an accept state, so we want our machine to be in that state. But since the machine, uh, it once it read A, since the machine read an A, the string ends. The string did not end with B, right? But the machine turned off, and this is a strange phenomenon. That is why we have to always assume and tell the machine where to move to next. Okay, this is simple as that. So here in Q0, once we receive an A, once we receive an A, it will move to the state Q2. We move to the state Q2, and why will it move to Q2? Because we know that in Q2 we are assuming that the next symbol that the machine is going to receive is going to be the this thing is going to be the final string symbol the machine is going to receive. The input it is going to receive is going to be A. So we start here, and if we receive a B, we tell the machine to go to Q4. Okay, tell the machine to go to Q4. Now the rest of the symbols here we define like that. We define uh, the machine to be in the next state based on this uh, starting based on these two symbols Q2 and Q4. Okay, so when the machine is in Q2, next symbol it will move to is Q1 on receiving A. Okay, next symbol, next state it will move to is Q1, and now once it sees a B, the next state the machine might be, if it is in Q2, The next state machine might be in is if it receives a B, is that it might be in the state Q3. Okay, we tell the machine to be in the state Q3. Why this is the case? Because Q3 means that let's remove this so it becomes clear. Machine input started with A and ended with B. Okay, we started with the assumption that A was final input, but actual output, actual final input here is B. Okay, so if we take a string AB, we will first say that move to Q2. Okay, move to Q2. Then we will say move to uh, Q1. Sorry, move to sorry. Yeah, move to Q1 because we started with A, but we have found B. Okay. Now here, if the string ends, okay, let's say if the string ends here, we started with A, we started with A, so we were in Q2. Now, if we encounter a B, we end it in Q1. Okay, this is where we are going to end it. Okay, Q1. So based on this, we will define our transition table here. So let's define it here. Q2, Q1, then Q2. Uh, Again, it will move to Q1 and Q4. It will, if it receives an A, it will move to Q3. And yeah, if it receives a B again, it will be in Q4. So I will fill the transition table here quickly. Just give me a minute. Q0. I hope you understood what we did here. And based on this transition table, we'll draw the transition diagram. So I'm ending this lecture here. tomorrow we are going to discuss Turing machine. And if the problem is unclear, I'll clear it tomorrow. Uh, Tomorrow it will become a little more clear on because we are going to study NFA equivalence. So yes, I hope you understand what we have done today. And yes, tomorrow we will revise the session. Thank you for attending.
Yes, thank you for your patience. I hope tomorrow you will join with the same energy. Thank you so much.
Welcome.